Alright, what's up, everyone? Second week. Hope we're doing well. I'm just gonna go straight to it. In linear algebra this week, I learned about parametric equations. Uh, they must be somewhere around here. The thing here is that this week I learned here over here. This thing I learned that this week I learned that in Khan Academy, at some point, for some reason, from here on, they don't have exercises anymore. Nowhere they simply don't have exercises, and for that reason, it gets really hard, to keep what you learned. So I'm probably not gonna be using Khan Academy as much, at least for linear algebra. Luckily enough, for Calculus 1, they seem to have exercises all the way to the end. So what I'm going to use instead is this book here that, well, it's Boldrini's book on linear algebra. I know it's Portuguese here, but I'm pretty sure it has oops, it has an English version. Uh, anyway, so parametric equations. I can probably show you here. Uh, Essentially, they are an equation that if you have two vectors, so let's suppose I have a vector here. I'm going to try to be very, very fast here. So let's suppose I have a vector 1, 2, and I have another vector here, 2, 1. And then, well, I can have an equation that goes through both these points here. So it would be something like this. I have the first vector minus and plus a parameter which is t times vector 2 minus vector 1. And then as you can see, I have this line here that passes through their points. Now, something that's even crazier is that I can actually tell uh, from the direction of this line. How do I do that? I can actually create a third vector um, and set its origin point to be the result of this equation when t is 0, and the final point, the result of this equation when t is 1. So this is not going to work here. I couldn't get it to work here, so I'm just going to copy the equation here. The equation is v1 minus plus t multiplied by v2 minus v1, okay? So when t is 0, this all goes away. So we're left with only v1. So the origin of our third vector here, okay, it's gonna be v1, which is, as you can see here, 1 to 2. And then its last point is gonna be when t is 1. So when t is 1, you're gonna have v2 plus v2 minus v1. Then v1 and v1 are taken off, and you're left with v2. So v2 is going to be 2, 1. And as you can see, let me take this off. We have created a vector that shows the exact direction of this line. It's going down. And let's say if I change this vector here to 7 and 3, I'm gonna have to check this too. 7, 3. Okay, maybe not 7, 3, maybe 3 and 3, and then 3 and 3 here too. And as you can see, the line changes, the vector changes. It's still going down, but well, it's something pretty cool to see. But and you might be asking, okay, what's the utility of this? Well, where is it useful one? What is the useful one? I actually did a little bit of research. I'm not 100% sure, but I think this is pretty useful in machine learning. Uh, I've heard that this is exactly how the machines learn. So essentially, the database of a machine is just a vector space, which I'm probably going to have to explain a little bit later. a vector space, and each data is a vector, and each axis, like the y-axis, the x-axis, the z-axis, and it can have end axis, uh, is a data type. So, for example, we can pretend that the y-axis is uh, name or age, and the x-axis is the job, and the z-axis is, I don't know, experience years. Those are data types, and one person can be expressed by a vector that is going to meet. So, for example, in this case, the person could be, I don't know, 3 is going to mean something, uh, and these other 3 is gonna mean another thing in our, in our data types. It's very complicated for me to explain this now. I'm just getting started. So, but I hope you understand. And then I have this. You have trillions of vectors, and you can use something like this parametric equation to know where all those vectors are aiming at. So I know that these two vectors, they're aiming down, but I could have uh, a combination of a lot of other vectors. There's a way that you can, increase this equation. A combination of all of other vectors, and uh, and you can actually find. I'm sorry for the horn. You can actually find out where they're going, and predict stuff. Anyways, next thing is how to tell if a set of vectors generate a space. This is basically basis of a vector space, but before I think we're gonna talk about vector space a little bit. But so vector spaces are, uh, well, the two-dimensional space is a great example, which is what we have here. You can imagine an infinite number of vectors here, an infinite number of vectors in different magnitudes, different pointing at different directions, and that's a vector space. It's essentially just a space. It has a limited or maybe unlimited amount of dimensions, and it holds vectors. And for a vector space to actually exist, to actually be considered a vector space, we can imagine a vector space as a set of vectors. Uh, and this set of vectors, it needs to follow these properties. So in this case, it needs to meet all these requirements. And in this case, u, v, and w, they're arbitrary, I think that's how we say it, vectors from that set. So, for example, u could, on the two-dimensional space, u could be ab, and then v could be cd, and w could be ef. You know what I'm saying? And then you do all those operations. A and b are real numbers, and they gotta return true. If so, then this set of vectors that you got is considered a vector space. I'm sorry for all these sounds. Let me mute this. And so that's a vector space. You can also have vector subspaces. Now those I need to study a little bit more. Like I said, I did study on Khan Academy, but I didn't get the chance to exercise, so it wasn't. I I can't exactly say that I learned it for real. But anyways, two bases of a vector space. Basis of a vector space is simply another subset, let's say like that. There's another set of vectors that are inside of this much larger set of vectors. So, for example, we know that this is the two-dimensional space is a vector a space, and you can have a small or big set of vectors that they do two things. Uh, let me delete this. So, for example, we can have a set of vectors that are simply 1, 0, and 0, 1. These are the classic ones. It's simply a set of two vectors in this case, And they do two things. They are linearly independent. So what does this mean? This means that I can take a constant a multiplied by v1 and take another constant b multiplied by v2, and that needs to give me the vector 0, 0. You know? Okay, this is the equation. And when I actually do this, I'm going to come up with a system, and a and b need to be 0. If one of them is not 0, then that means that one of the vectors inside of this set of vectors could be much larger, by the way. One of these vectors, at least one of them, is a linear combination of another vector. What we're doing here is essentially a linear combination. We are multiplying constants by vectors and summing it all up and getting something else. So sometimes you can have a vector that's just a linear combination of another vector in that same set, and that's gonna, well, ruin everything, and that set is not gonna be linearly independent. So that set cannot be considered a base, or those vectors cannot be considered bases of that vector space, because they're not linearly independent. That's the one thing they do, and the second thing they do is that they generate the whole space. So, well, we know for sure that v1 and v2 here, they're like the basic bases of the two-dimensional space. So we know that they generate any vector here using a linear combination. But if we were to prove that, which I can't do it here, it's probably better on a paper. What we have to do is we need to imagine an arbitrary vector here that belongs to this vector space. So AB is a two-dimensional vector, so it belongs to the two-dimensional space, and we gotta. I'm actually gonna put this as x1, x2, or maybe even better, xy, so it becomes more clear. And that's going to be the linear combination of these two vectors, so AV1 plus BV2. And if that actually turns out something, because x and y are numbers, but not in this case because they're proving them, so they're literally anything, literally any number that you can ever think of. And AB, they're constants that they need to, you kind of need to tune them to multiply these vectors that you already know. You're trying to prove them that we're trying to prove that they generate the space. And again, of course, we're gonna end up in a system. The target here, the goal here, in this part of the process, is you need to get an equation for A and an equation for B. If you get that and it works out, this means that V1 and V2, they actually generate the space. So for example, A could be, I don't know, 2 times X plus B, something like that, you know what I'm saying? So we're going to have an equation for A, you're going to have an equation for B, and then if you actually turn these into numbers, so let's say 2 and 3, you're going to put them and whatever else you need into the equation for A, you're going to get an A, it's going to be a number. You're going to put everything else that you need in the equation for B, you're going to get B. And then you multiply A times V1 plus B times V2, and then actually in the end you're gonna get exactly the vector that you're looking for. So this means that the vector 1 and vector 2, they can generate any vector in this space. So they are a base of that vector space. At least that's what I understood. Anyways, to calculus now. So I got a little deeper into left and right hand limits, because usually when you have a 0 by 0 limit, you're just gonna say that it does not exist. But in fact, I actually have parametric equations here. But in fact, that's not always true. Sometimes, I don't know why it's Portuguese. Sometimes I'm trying to find here. Yeah, it's not here. At least not with the name I gave it. Anyways, so you have essentially you have two limits. In fact, you have a limit of an f function divided by by a g function. It turns out that the f function is undefined and the g function is undefined too, or maybe they are defined but it gives us a 0 by 0 division which does not exist. Does that mean that the limit does not exist? No. What you need to do is you need to check the left hand limit of the f function. It's going to give you something, and divide it by the left hand limit of the g function. That's going to give you another number. And then you do the same thing for the right side of f, right side of g. You divide them two, you get another number. If that first number we got is the same as the second number we got, then the limit of f divided by g is that same number. I hope I made myself understandable. So basically, it's just there to say that it's not because a limit is gave you a 0 by 0 that it is undefined. Not always, at least. Limits of a compositive function. I don't know if it's here. Yeah, it's here. Basically, we have a limit of a function that is, something like this. You have a limit. The limit when x goes to something of g h x. So you have a function, and I have another function inside of that function. And okay, how do I solve this? What we're gonna have here is you're gonna have to I'm gonna have to calculate the limit of hx, and that's gonna give you something, and then I'm gonna put that something into g, because this is also the same thing as if you put g and the limit inside of g. But sometimes that might not work. So if it does not work, what we're gonna have to do is we're gonna have to do the same thing. So we're gonna have to check the left hand limit of h, put that into g. So the left hand limit of g when g receives those values from the left, and then the same thing to the right. Now there's something very interesting about this, is that, for example, let's suppose I have this function here. I'm gonna make it like this, look this. And okay, so let's say we had usually you have two functions, you know what I'm saying? And let's say I have the left hand limit of h gives me numbers like 0.01, 0.001, 0.001, I'm saying, and I'm gonna put those numbers inside of g, also following the limit. So this is g, and I'm gonna put the numbers here, shorter numbers of x, all the way to 0, and I'm gonna see that it tends to 0. Okay, and then what I'm gonna do is I'm gonna do the same thing for the right hand limit. So the right hand limit of h, let's suppose it also gives me numbers that tend to 0, but on the right side, so positive numbers. And then I'm gonna put them inside of g. So I'm gonna do the limit of g when you receive numbers that are close to 0 but on the positive side. And what we're gonna realize is that they also go close to 0. So both sides go to 0. So this means that the whole limit is 0. It's kind of complicated to just do this, but if you wanna take a better look for yourself, I'd recommend Khan Academy here. At least for calculus, I'm not sure about linear algebra. That's compositive function. I can also learn about direct substitution, which is probably down here. This is basically like you have a function, let's say the limit of x minus 3 when x tends to 3. there's nothing that could possibly go wrong with that function. Limit of x minus 3 when x tends to 3. Yeah, for some reason that no, okay, 0. So like x minus 3, what could possibly go wrong with this? You're not dividing it by anything that could possibly go to 0. So all we gotta do is just put 3 in the function, and that's gonna be the limit. That's what direct substitution is. Limits of trigonometric functions, not very complicated. You can have like the limit of the sine function when x tends to pi. So you know it's kind of like direct substitution. The sine of pi is 0, but you can also have left and right hand limits for that type of limit. So for example, let's say a limit of x, the limit of the sine function when x is tending to pi. That's not a good example because, yeah, but you get what I mean. That's going to give you 0, but that's going to give you numbers, that's going to give you positive numbers if we're going from the right, I guess. It's going to give you positive numbers all the way to 0. But if you're coming from the left-hand limit, that's going to give you negative numbers all the way to 0. So you got to be paying attention to that. And same thing for the cosine function. If you have the limit of cosine function when x tends to pi, cosine of pi is minus 1. But if you're going from the right, that's going to give you in fact, in both sides, now that I think about it, in fact, in both left and right hand limits, those are gonna give you numbers, greater than minus 1, but that tend to go to minus 1. It's something you're gonna have to check for yourself on a paper, but it's something really interesting to think about. Anyways, piecewise defined functions. I'm trying to do this fast here. How many minutes? I don't know if I can check this here. Oh, 22 minutes already. Hope I'm not wasting your time. Piecewise defined function. So here in this side, let me actually go the other place here. No. Wait. Oh, here. Because this is in English. So if x is below 2, return x squared. And so you can see that it breaks when x is equals to 2 and on. And effect of 0. So as you can see here, I have a piecewise function. This means that it breaks and turns into something else from a certain point on, and that point is 2. And then you can very easily have the limit of that function when x tends to 2. What is that? That simply not gonna exist, because you can have the limit of the left hand limit of that function, that's gonna give you 4. The right hand limit of that function is gonna give you, I suppose, something like 0.9, I suppose, 0.9. But maybe you can have something like, let me change this a little bit. Something like this. Let's pretend that they're together here. What's going to be the limit of this function? No matter if they change the behavior, both sides tend to 4. Let's pretend at least. So the limit of this whole function is going to, when x tends to 2, is going to be 4. That's piecewise defined functions. Limit solved by factoring. Now, I'm going to give you a quick example here from my own notebook. It's going to be limit of x squared plus x minus 6, exactly, x squared plus x minus 6, x minus 2 when x tends to 2. It gave us 5. That answer is correct. Okay, but like when you look at this and you try direct substitution, so you try to put 2 here, you see that we're trying to divide something by 0, and that's not possible. So what do? This doesn't mean that it's undefined. It just means that you gotta manipulate the equation a little bit. How do you do that? You try to factorize. I don't know if that word exists. You try to do something with this, and we know that x squared plus x minus 6. You can express that as x plus 3x minus 2, because then you can have x squared, 3x minus 2x is going to be x, and then 3 times minus 2 is going to give you minus 6, so they're the same thing. And then, as you can see, you're going to have this over this, and then what we can do is you can cut x minus 2 with x minus 2, that's going to give you 1. And then you're going to end up with the limit of x minus 3 only. The limit of x minus 3 is direct substitution. It's just going to put 2 here, and you're going to have 2 plus 3, that's going to give you 5. That's factoring. And right after that, I'm sorry again for the sound. Right after that, you can have the limits by rationalizing. Essentially what that is, you can have a limit of a function that at some point it has a square root or something like that. So let me check an example here. I have this example here, x plus 1 divided by the square root of x plus 5 minus or plus 2 minus 2 when x tends to minus 1. So as you can see here, or I gave us the answer, which is 4. Yeah, it is 4. When you try to do direct substitution here and you try to put minus 1 this x here, you're gonna have the square root of 4, which is 2, and I'm gonna have 2 minus 2, which is 0. So we're gonna have division by 0, not possible, but this doesn't mean that the limit does not exist. What we're gonna have to do here is rationalize this limit, this equation here. Well, now what does that mean? This means that you're gonna have to multiply both sides of this division here by the conjugate of the side that has the square root. In this case, this means, okay, what is the conjugate of this? This means that if you, in a very basic way, this means that if you have a minus here, you need to switch it to plus. And if you have a plus, you do the opposite. So what I'm going to do here, I'm going to multiply this by the square root of of x plus 5 plus 2, and the same thing on the other side. And now why would I do this? This is based off on this. A plus b times a minus b is equals to a squared minus b squared. Because have a times a, then a times minus b is going to give you minus ab, and then plus ab, they're going to cut together, it's going to give you 0, and then minus b squared. But it's not. That's not exactly what matters here. What matters here is that you have the square root of x plus 5 squared. So we're gonna simply get rid of the square root. So rewriting that, we're gonna have on the top side, we're gonna have x plus 1 times the square root of x plus 5 plus 2, and on the other side here, we're gonna have is the square root of x plus 5 squared, which is going to give you x plus 5, and minus 2 squared, which is going to give you minus 4. You need to be very cautious of when you have need to be very cautious of when we have like minus x squared. This is x squared, but negative. Okay, this is not negative x squared. You know what I'm saying? Just be careful about that. And then 5 minus 4, that's going to give you 1. So you're going to have x plus 1. And as you can see here, okay, we turn all of that into this. You're going to have x plus 1 times, square root of x plus 5 plus 2 divided by this. Since they are multiplying here, we can cut the x plus 1 here and the x plus 1 here. And all you're going to have left is x plus 5 in square root plus 2. All you got to do now is some direct substitution. When you put minus 1 here, we're going to have 5 plus minus 1. This is going to give you 4. Square root of 4 is 2. And then we're going to have 2 plus 2. I'm talking about the thing going on over here. 2 plus 2, that's going to give you 4, which is the value of the limit. Again, try to do this on a paper. You're going to understand me way better if you do this on paper. And okay, that was limits by rationalizing. And lastly, because my voice is already it's already gone, Python. Now, something very good about Python this week is that I finally learned Python object-oriented programming. I was very excited to learn this. So yeah, I finally did. So yeah, so the introduction was basically, how can you create a class? What is a class? What is an object? A class basically defines a type of behavior inside of your code, and you can have methods, you can have variables, you can do a bunch of stuff. You can even customize the way that the own language works, kind of. And so we create a class. You can name it here. So class, name of the class. And then we're gonna have this function here, which they call constructor. It needs to be called exactly this way. So dunder, init dunder, and it's gonna take these arguments. The first one is our self, which is the object itself, and it's gonna return it. And yeah, that's it. And then you can set up the arguments that you have here inside of the object. So essentially, what we have here is an object with all those properties that you can see here. I created an object. How to become a billionaire by the secret billionaire 2026, 1,500 pages. And then I asked to print the title of the book, and it gave me exactly what I said as the title. You know what I'm saying? So yeah, it's kind of like a dictionary, but kind of better because I don't have to mess around with methods. Inheritance, methods here. You can put some methods inside of the class, but you can also have class variables again. Of course, they're kind of like they are attached to the class. But class inheritance. So basically, what this means is that sometimes you can have a piece of code that can be inside of a class that can be used in other classes. So for example, here I have a class human, and down here I have a class coder. Well, coders are human, and they also eat, they also sleep. They don't always sleep, but well, they can sleep. So I can inherit all this stuff here from human, doing like this. So class coder, when I'm defining the class, I can use between parentheses, but the name of the class that I want to use stuff from. And then, as you can see here, I can create a coder here, putting the arguments of human, and use the methods from human. And you can also have multiple classes here too. But then I came when I was writing this, I came up with a problem. When I try to have a init function here, when I put a init function here, because I wanted to have different arguments like mother language, years of experience as a coder, whatever. Whenever I called coder again, I couldn't have a name and age. It didn't run the init function for the human. It didn't run the constructor for human. It only ran the constructor for coder, and that was bad because I also need a name and age. So what happened after is that I learned about super function. The super function is actually very super powerful, and what it does is that it can run and read stuff from the class that you're inheriting. So essentially, what we're gonna have here. So for example, here I have a down here I have a shape class and I have this square class here. Now square is a shape too, so I'm going to inheriting stuff from the shape class. And then I have the constructor here, color, field, width. Now if I only had this init here and I call it square without color and field, well, it wouldn't exactly work. What I'm trying to say here is that the only way that you could possibly run this code to have a color and field is through the super function. The super function is gonna let everything from here available for you to use here. And then I could run this init here, this init here, is this init here. And I'm running it inside of another class. So I can set color and field, the color and field properties inside of this object that I'm currently constructing here, which is the square. That's what the super function is, basically. Static methods, they're basically, then you can need to use this decorator here, which I learned a little bit about. They basically change the behavior of methods, so they behave it as another way. Static methods are basically methods inside of a class, they're placed inside of a class, but they don't need, because usually when you have a method inside of the class, the first argument is always self, which is the object. So you're obligated to provide an object for that function or for that method whenever you need it. But sometimes you need the method from that class, but you don't have any object, or you don't need to provide any object. So what you do is you create a static method, and static methods, they can have any type of argument or even no arguments at all. So as you can see here, I had a course argument, but I didn't have the self argument. So I can call this without even having created a student function before. Class methods, now they're similarly to the static methods, they don't take the self variable, and don't take the self argument. They take the class argument. So we can put a class here, and then it can access stuff from this class and print in a different way if you want. This could be very useful. This means that you don't have to create objects before using this either. Then magic methods. They're basically methods that are called by default by Python whenever you do something normal in Python. So for example, whenever you create a car function, whenever you create a car here, so I created a class car, whenever you create a car here, whenever you call this, it's gonna run this definite function. But notice how I never called init anywhere else here, never did car.init, because Python does that automatically for you whenever you create an object. So that's a magic method. And then you might think that okay, that dunder init is the only magic method, but it's not. There's a ton of other ones that they're just not defined. And then if you need to have a specific behavior for your class, you can define them to do something. So for example, whenever you print an object, it's going to give you the memory address of the object. But let's say I have a car here. Instead of whenever I print the car, instead of the memory address, I want to print what did I do here? The model and the year and the color, all the properties, or maybe not all of them. You can literally go crazy with this. You can do whatever you want with this. All we gotta do is just define dunder string, and then going to take the object, of course, as argument, and then you return what should be printed. So whenever I print a card that I just created, it's gonna print exactly in the format that I told it to. You can also have the method dunder equals. So whenever trying to do comparison operations, with two objects from the same class. Usually, if you don't have this defined, this is just gonna give you false because even if they have the same properties here, they were two objects created in two completely different times. They have completely different memory addresses, so yeah, they're pretty much different. They're pretty different, but you can set up define in dunder equal function that's going to take the self object, which is the first object, and the oh my god, sorry. Where were we here? And the other car, which is the second object here, and you can return true or false or even another completely different thing, maybe a string saying yes or no, based on your own criteria. In this case, the class car has model, year, and color, but I didn't even count the color. If they're the same model, they're the same year, then it's the same car, and then it's gonna return true. Well, I have a full-on. There's a full-on site on all the methods that you can use here. I'm gonna put this link here on the description, and then finally, because my voice is already it's already hurting. The property decorator. So basically, I just learned this just a few hours ago, so I'm not 100% great at it. I didn't even get the chance to implement it on something. So I'm gonna try to explain, but I can't promise anything. So basically, what we have to do, of course, you're gonna have to have the the property here decorator. And what this means is that this is very useful apparently for when you have private variables. Now, private variables, they're variables that they are set into the object using this underline before. This means that, well, technically, they shouldn't be accessible from outside of the class, only from inside the class. But they are. I don't know. I'm gonna have to read about that more. Anyways, and then you can create this, set up this as a property. So def password. So whenever you try to do something with the property here, like print it, it's gonna follow this function. So, for example, I made a desktop class here, and then you can, whenever you create a desktop, you can have a password. And when you're trying to print that password, of course, password is a sensitive information, so I wouldn't just like it to be printed. So instead, it prints an asterisk as much times as the length of the password. So here I created another desktop. The password is high, and then I try to print the desktop password. Instead of just returning high, it returned two asterisks. You can have the password setter. Now that's when you try to change or set a property, and you're gonna have the same name for the function. I don't know if you can change this name. I'm gonna try that later. The object and the new value for that property, and then maybe when the user is trying to set up a new password, I'm gonna check if the password is the same as the password that's already in the system. So if new password is already equals to the password that I'm already holding, let's say like that. Notice how since I'm inside of the class, I need to use the underline here because I'm accessing the private variable. And then I say okay, and then just print. You can use the same password, return. Otherwise, update the password. So here, create a desktop, password high, and then try to set the password to high, and well, it shouted at me, and then I tried to set the password to something else, and it didn't complain. And lastly, finally, is the property.deleter. Now, I'm pretty sure there are a lot of other, things here, but I stopped at here. So password.deleter, that's basically when you try to delete a property from a class. So add password deleter, define password again, and the only argument that you receive is the object itself, and then delete the self delete self the password. So here, create a desktop, set the password as high, and then try to delete the password from the desktop. And very interesting, when you try to print the password again, it's gonna give an error. So yeah, it was really deleted for sure. I'm pretty sure all those things, they all have a very crucial role in actual big softwares. Just very hard, uh, to learn these things. And okay, where is that even 1% useful? You know what I'm saying? I'm feeling like that with all those things, but I'm pretty sure that eventually they're gonna become useful. Anyways, probably half an hour here, just talking. 45 minutes just talking. Oh my god. Thanks for watching. See you next week.